So today we'll be talking about facial sentiment recognition using deep learning. So deep learning is a subset of artificial intelligence, and basically what we're going to do is we're going to observe a face of the person, okay, and we're going to be able to accurately understand which emotion he or she is currently feeling based on the expression. Now this should be real time, obviously. So for it to be real time, we'll obviously need to use our webcam, and the model will have to be trained on either lots of images or bits of video. Now training a model on real time video is actually not sensible, because at the end of the day you have to actually break it down into frames, so it converts it into so it basically ends up converted to images anyways. Okay, so let's get into it now. So currently, let's see what problem exactly are we trying to solve with this. So uh, currently, the way things are, emotional intelligence is currently absent in systems, like in any digital system. Okay, which limits basically the ability of the user to understand and relate to the digital system he is currently interacting with, be it in education, healthcare, customer support, right? If you look at the case of education, right? If you are using some, if you're proctoring a test, or if you are trying to, so for example, in a practice test, right? Or let's take a different example. When a teacher is conducting an online class and you have several students attending it, they're not 5, they're not 10, it's like 20, 30 plus, sometimes 50, right? One teacher alone cannot possibly keep a track of 50 children and whether they're all understanding what's being taught. And because of that, what happens is there's a gap in the classroom. Some students are really being paid attention to, and these are usually the bright ones, but some other students who are perhaps not on the same level because they missed some classes earlier, or some because of some circumstance they're not currently able to understand what's going on. They don't actually speak out and say, okay, we're not getting this. Instead, that topic ends and the student ends up confused. So if you had an emotional, a sentiment recognition engine, which could actually just looking at the face be able to flag that, okay, certain this student, okay, student with the enrollment number 21 looks confused. So then the teacher can actually pay attention to that particular student and make sure that, okay, he is on track, right? So this would really help in the education area. It would also really help in the healthcare area. How would it help in the healthcare area? Well, obviously, in therapy, it could be a huge help when you're going through mental therapy. Obviously, when patients are, the ones who are speaking, then you can have this system which can analyze the patient's facial expressions and then detect the emotions. And using that, it can also help the therapist to actually do a better job than they normally do, right? Same for customer support. When you are speaking to a client, it would be better if you actually knew how the client is feeling at that moment in time. See, when they get annoyed, if you actually knew that they are getting annoyed before they actually, have a, they go through an outburst, you could, start, what do you call it? Basically, you could modulate your tone to make sure that, the client feels at ease, right? So these are just some basic problems which are caused currently because of because digital systems lack the ability to understand human emotions, but which can be solved in the future. So currently, if some student doesn't understand and is confused, he you cannot expect one person to be able to monitor everyone, right? So that student unfortunately ends up not getting the lesson, not able to understand that concept. Same goes for if someone is feeling disconnected during therapy, you will never be sure of it, right? Or if you look at customer support, where outbursts do happen, customer support has to deal with those kind of problems, and then when people get aggravated, they want to be put through to the manager, and then it's escalated, so on and so forth. So it would be easier if you had some emotional recognition system which could actually give you a good idea as to whether the client is on board with what you are saying or not, and to what extent, right? Another example is for healthcare is that you have a lot of patients who are sedated, right? So they are in a non-verbal state where they can't really speak out. So if they are in pain, there is no way to know because they're not going to make any noise or anything. They can't move much, but there will be expressions, okay? Because even when you are passed out and you feel pain, there are some involuntary expressions that your face will make. And if you have this sentiment recognition system online, it can observe the patient, and if it notices such involuntary expressions, it can actually alert, and this can actually save many lives, and can also save a lot of issues which happen, because usually what happens is in the ICU, since they're not always being monitored 24 by 7, sometimes the patient goes through pain, and the doctors, they find out a tad late. It would be better if they knew earlier on, right? So that is the problem that we are dealing with. Mainly, it's useful for ed tech, health tech, customer support, but there are obviously other applications of this as well. It's not just limited to these three fields. Next, we have what our solution is going to do. So basically, on a very basic level, if I'm talking right now, all our engine is going to do is it's going to detect and classify the emotion. Okay, it's going to look at a frame, a picture, detect the face in the picture. Okay, analyze the expression, so it's going to figure out exactly how this user is feeling. There will also be a confidence percentage, and we'll discuss as to why confidence percentage is important later. And then it will classify that expression, alert, if there's an alert setup, then it will alert the person on the other end who's dealing with the person being observed, and so on and so forth. So that is our basic solution on a basic level. Now, the idea is there is a sentiment recognition, not exactly I would say sentiment recognition. There is uh, a convolutional neural network. It's a family of convolutional neural networks, CNNs, which are developed by Google. Okay, it's called EfficientNet. What is a CNN? CNN is basically the type of neural network which is used to work with images. So whenever you want to detect objects and images, in this case, you want to detect faces before you analyze the expression. You want to actually detect the face in the picture, right? Because the face doesn't take up the whole frame. So what EfficientNet will do is it will detect the face in the picture, okay, and then what we're going to do is we're going to train it. Okay, so what happens is EfficientNet will be taking it pre-trained, okay, and then we'll do something called transfer learning, which is what happens is you in a neural network you have layers, okay, so you will freeze some of the layers, and the rest of the layers you will retrain on some new data. Okay, this data will be more applicable to your use case. So in our case, it would be like the FER-2013 dataset and the AffectNet dataset. FER means facial. FER dataset is stands for the facial emotion expression recognition dataset. Okay, it was made. There are two versions, if I'm not wrong. There's a 2013 version and 2015 version. We'll be using both. And there's also something known as AffectNet. Okay, AffectNet is also a data set which is used for basically detecting. Basically, it's again for facial emotion recognition, where you have faces and then you have labels. The labels are basically the expression on that face described. Whether the person is sad in that picture, he's happy, he is anxious, he's worried, is he angry, so on and so forth. What we are looking for is basically anywhere close to a 92 to 95% accuracy, which is what is possible. Okay, we can test it out, and in 92 to 95% accuracy is possible when you're trying for a system with efficient net which can achieve facial sentiment recognition. And we'll be using webcam inference, which means you'll be taking live data from the webcam. At obviously, because it's a webcam, it can't take data at the rate of 120 frames per second, because that would firstly become too heavyweight. Your model will become slow if it tries to process that many frames. But I think 30 frames per second should be good enough, right? That's basically a frame. it's 30 frames per second is like good enough. Okay, that's 30 frames per second. So any slight changes in the facial expression will be detected well enough with 30 frames per second, while keeping the model lightweight and speedy enough, right? Which is important. After all, you don't want delayed delayed output from your system. That can be problematic over here, right? Here's a chart we have of basically, each industry and the projected market value by 2030. So as you can see, you have EdTech, which has a projected market value of $25 billion USD. Then you have Health Tech, where again it's vital. Surveillance, obviously surveillance. Basically, if you're monitoring the facial expression, you can figure out if someone is nervous, which could be an indicator that something shady is either going on or is about to happen, right? The VR, AR, basically the virtual reality, augmented reality space. Again, there also it has a huge practical application, and amongst them you then have other industries, right? We discussed one of the industries as customer support, so on and so forth. Here we just have some figures which are predicted about how much this industry is projected to grow, so on and so forth. We basically, what we have researched, there is a 17.4% CAGR, CAGR being your compound annual growth rate of 17.4%, which is huge. Okay. Our model has achieved between 88 to 92% validation accuracy, which is really good, but it can be improved much more to somewhere above 95%. And we have ideas for that. We know how to get it done, and we will also, show what steps we have in mind. Real-time responsiveness: the engine processes data at 15 to 20 fps. It can also process data at 30 fps as of now. In the future, if required, we can obviously test out if we can go for 60 fps or not, but for now, anywhere between 50 to 30 fps we can work with that. The pipeline is easily deployable, which means what we've done is we've split this into different APIs, which makes it really easy to handle. Right? It's not one huge monolithic structure. We have divided it into several components at a microservices level, which makes it easier to, test, deploy, maintain the integrity. It makes it easy overall to manage this entire structure, which would otherwise become too much to handle, because there are more components which we haven't discussed yet to this entire system. There are obviously others in the same. Basically, we have competitors here as well. Like there is this company known as Affectiva. Okay, they too are looking for using emotion AI for automotive safety, so on and so forth. You have you have a company known as Real Eyes. Apple has Face ID currently, which is currently just 3D face mapping for security measures, where you can only enter the device if you are identified as the user or someone who the user has allowed to access to the device. So yeah, currently Apple is not using sentiment analysis, but yeah, face detection is they're using that already. Microsoft Azure Face is a cloud-based facial recognition system where basically all the data is live streamed through the cloud, so all the heavy processing is done over the cloud. Okay, this is for enterprise level integration. And then you have Amazon's version of the same, right? Real-time inference though is only offered by Microsoft and Amazon currently. Accuracy is somewhere around 80%, as was estimated previously, anywhere between 80 to 88%. Their model architecture obviously is proprietary. We are not only going to use efficient net, right? Even we ourselves will not just be using efficient net. We will be using other models in sync, which together will become, it will be multi-model basically. Okay, transfer learning, basically if you have data of your own which you want to use for this, you have your own data which you want to feed. Sure, we can get that done. The others, they do not allow you to customize the model, which means there is no transfer learning capability. So even if you do have your own data, you cannot use that to optimize the model for your own usage. Dataset diversity, well, we are not only using FER-2013, FER-2015, AffectNet, CK+. Is another sentiment recognition, basically facial expression recognition data set. Okay, we are using a lot of different data sets which have a lot of different data points, a lot of different pictures of a lot of different people across ethnicities, races, which basically allows diversity. So the model isn't thrown off if it finds some, basically it's not thrown off by different ethnicities or gender or so on and so forth. They're making sure that the model works and provides optimum performance across different situations, right? We have offline deployment to a certain extent. Okay, and obviously our model is customizable, which means if there are some changes, then we can get those done. Cost depends on the use case. We don't have a fixed cost. It depends on what level you want to deploy this model at. A little more about our data sets which we are using for this AffectNet, which has about 1 million labeled facial images. We also have, in that we have 8 emotion categories. You have happy, angry, disgusted, etc. And we have high diversity in lighting, positioning, ethnicity, expression, so on and so forth, right? Giving it very varied data so that we can make sure it works across different environments. FER 2013 has grayscale 43 by 43 images. Uh, my bad, 48 by 48 images. It has 7 classes for emotions, not 8, 7 classes. And it's widely used for benchmarking. So basically measuring the accuracy of a sentiment recognition engine, right? And then you have CK plus, the extended Cajon Canade data set. It has sequential images transitioning from neutral to peak emotion. So this data set gives you more insight as to how emotions transition, right? How you go from neutral to a certain emotion, which gives the model more insight into how to detect a particular sentiment. It also again has emotion labels. It also has something called action units. Action units basically, they give you the movement of each individual facial muscle or group of muscles and how they correspond to the final outcome, right? So the how much each facial muscle twitches or moves basically, and which expression that ends up with, right? That is what it gives. So it gives you a deeper dive into basically understanding. It gives you basically a deeper, it gives your model a deeper understanding of how the emotions evolve over time. Okay, so those are the data sets we are using. There are more, but these are the main three which should be mentioned. Now, when we take input from the webcam, right, or when we are working with our data, what we're going to do is we're going to normalize. So basically, when I'm working with my data, what I'm going to do is I'm going to normalize the facial images, right, which is basically scaling kind of, so that pixel variance you have, in pixels, every image is made up of pixels, right, and each pixel has a value anywhere between 0 to 255. And then you have RGB channels. So you have a value between 0 to 255 for red, green, and blue. And what you want to do is basically scale these to a range between 0 to 1, which makes it easier for the model to function and results in more accurate predictions. We'll also be resizing all images to either 224 by 2. Currently, we are planning to resize all images to 224 by 224 pixels. But yeah, depending on the data set, we might opt for a different value as well. We'll be augmenting the data using techniques like horizontal flipping, vertical flipping, zooming, rotating, adjusting the brightness and contrast to make sure that the model. So that's basically to give more varied data so that our model can work with different kinds of data in different environments, basically making the model more robust. The labels will have to be encoded, so we'll be converting them to one hot encoding vectors, where basically instead of saying 1 for happy, 2 for sad, 3 for angry, what we'll do is we'll have 8 different categories, and then we'll have how confident the model is that this person is angry, right? So for example, it's 50% positive this person is angry, 10% positive that this person is worried, so on and so forth. So we'll get exact confidence ratings for the person. And obviously the final tag, the final output will just be the emotion which the model is most confident that this person is currently experiencing this emotion, with the confidence score about how sure the model is, because that is important. Our backbone of the model is obviously EffectNet B0, which we'll be using transfer learning with. We'll be modifying the output layer because we have a multi-class classification going on here where you have 8 different categories, 7 different categories. We'll be using softmax. What softmax does is, instead of having your output confidence scores such that they add up to a value above 100, which happens, it makes sure that the outputs are normalized such that when you add up the confidence scores for each emotion rated by the model, it adds up to 100%, which makes more sense to us, right? um, Loss function. So when you're creating a neural network for any task, you need to decide what will be your loss function. And for our model, since we have multi-class classification, which means we are trying to sort people based on their facial expression into 8 or 7 different categories, whether they're angry, sad, happy, which emotion they're expressing. This is multi-class classification, so for that the loss function you should use is categorical cross entropy. We're using the Adam optimizer, which basically works in batches, takes batches of data and processes them one at a time. You could also use SGD, stochastic gradient descent, which takes only one image and works at it at a time, which makes it faster, but there's a lot of noise, which means basically the weights and the biases in the model are being changed very erratically, because one image causes a huge change, the other image can cause the polar opposite change. So there is a lack of generalization, which results in a lot of variance. Metrics we're using are accuracy, precision, and recall. Okay, basic metrics. Batch size is 32, which means that at every basically at one time we are processing 32 images. Okay, which also works with the number of frames per second, 30 frames per second, right? So our model can actually process that number of frames in a second. You know, every second it can process that number of frames. And when we're training the model, we'll be running anywhere between 300 to 500 epochs with early stopping and learning rate scheduler, which basically means if the model sees that the training accuracy or let's say training loss, so if the model sees that the training loss is decreasing but the validation loss is not, which means the model is about to overfit, it stops. That's what early stopping does. LR scheduler is also known as your learning rate scheduler. Basically, when your model gets on a plateau, which means your validation loss is not increasing or decreasing much, it instead of where it senses that we are just stuck, what it does is it increases the learning rate. But if it senses that there is a movement about to come, right, that either the error is about to increase or decrease, it decreases the learning rate, because you don't want to go too fast. Even if your error is increasing, definitely you don't want to go fast, you want to reverse. And if your error is decreasing, which means your error is actually reducing, your model is learning, you don't want to go too fast either, because then you might actually risk missing the optimum value. We'll be cross evaluating across data sets. Obviously, the testing will be done across all data sets. We'll have validation and testing sets in all data sets. Okay, we will obviously generate confusion matrices, classification reports, so on and so forth, and these will be class wise. So for each emotion, we'll measure how good our model is at detecting each emotion. We'll also be evaluating how good our model performs with each ethnicity, so on and so forth, to make sure that there are no gaps in the model performance, right? It should be good at understanding how a child's emotions as well as an elderly person's emotions, as well as a middle-aged person's emotions, right? So across ages, across ethnicity, across uh, emotions, we will evaluate that there are no gaps in this model, right? And so we'll test it separately on subsets of the data for generalization. For real-time inference, as I said, we'll be integrating with webcam access, which means we'll be using OpenCV, which what it will basically do is it will detect the face in the image and pass only the cropped face. Okay, it will crop out the face and only pass that to the model, which obviously reduces background information and noise, makes processing faster. Okay, the prediction will be displayed on a bounding box. So the face will have a bounding box around it, and on that you'll have the prediction, which is which sentiment the user is displaying and the score for that. Uh, Frameworks which we'll be using will involve TensorFlow, Keras, PyTorch, OpenCV, so on and so forth. Here you have the different API endpoints which we'll be creating. So there will be one which will be a post endpoint, a what's it called? Your post request for predicting an image, right? So if a user just provides an image, or you're just training your model and you just want to provide it with an image, this is the endpoint your data will go through. When you're trying real world webcam inference, you have a different endpoint for that. This will be the predict webcam endpoint, which will receive immediate, from where you can receive immediate emotion analysis from live, real live streaming the data. You have a batch prediction endpoint, where you can basically in the future, if you want to, you've collected more data and you want to train the model on that as well, you can use this endpoint. You have get model info, which will basically give you the information about the model, which version you're using, what is the name of the model, which in this case you won't get the name, you'll actually get the architecture because it's multi-model, but yeah. And then feedback is very important, because if the model is going off, either the user himself who is being observed by the model, or the person who is dealing with the user. So in the case of customer support, the customer support agent who is dealing with the employee, they have to actually give feedback on how well the model is performing, which the model will then use to either improve, and basically improve on its faults or errors. And if the feedback is positive, obviously the model understands that it's doing well, so it doesn't have to change anything. But mostly when there is some, the model is not actually performing as expected, and you give it some feedback, then it will adjust itself. There are explainability tools. We are using SHAP and Lime, which are the two most important ones. What are explainability tools? SHAP stands for Shapely Additive Explanations, and Lime stands for Local Interpretable Model Agnostic Explanations, right? So, what that basically means is SHAP can exactly explain why the model predicted a particular emotion from a face image, right? So it can explain exactly why the model predicted that this person is angry and not worried instead, right? And this increases transparency between the user, which is your enterprise, or the user itself, and the model, right? So it gets more of an idea as to why our model is saying you're angry, or so on, and or the person who you're dealing with was about to get angry, right? It also helps identify model bias. So if the model is repeatedly making a mistake in some area, this allows us to identify it. Lime, basically what it does is it, so on the entire face, there are some parts which are more important when you're trying to predict the emotion than others, right? Some very important parts are the areas around the mouth, right? The eyes are very important. So some areas are very important, and particular movements. So apart from just identifying the key facial regions, you actually also need to understand which region, which type of movement in which region usually leads to a certain label. So, for example, when someone's upset, the corners of the mouth start drooping on the lower end, right? So, or if someone's happy, then obviously the mouth curves up in a smile, you have wrinkles around the eyes get kind of scrunched up. Such evaluations basically are done by Lime, so it can let for a happy prediction, the model is currently focusing on the corners of the lips and raised cheeks and the area around the eyes, right? So this gives you more of an idea as to which regions are positively influencing a label and negatively influencing a label. So in the case of, if you give it a picture and say, okay, the model predicted happy, why did it do so? It will say, okay, corners of the lips, raised cheeks. Okay, these are green regions, which means if the cheek is raised, if you have this scrunch near the eye, if the corners of the lips are raised, that is green, which means it's a positive influence, which means the chances of this person being happy go up. But if you have lines on the forehead, chances of that person being happy go down, that is a red region, so on and so forth, right? This is done with Lime. Okay, so from Lime you can actually import a specific module known as Lime image, which works with basically creating those boundaries on an actual image. And we also have the practical, we can give you a basic idea of how the practical implementation for that works as well. Obviously, for any AI system to perform well, it has to be ethical, right? And currently I know my window is actually blocking out one of these points. There are four main points: there's ethical audits, there's bias testing, informed consent, which is the one actually being blocked out. So if I move, I can't. Okay. Informed consent and transparency and oversight. Okay. Ethical audits basically means that you have to regularly review the model and make sure that there is no bias, right? Which again also comes in bias testing, where you have to make sure that you're utilizing your data sets are balanced, right? Which is something we are really focused on, because the model only performing well on a particular use, particular environment, performing well in a particular environment, or with a particular ethnicity or gender or age group, that is not what we are aiming for. What we are aiming for is a heightened state of multimodal performance across environments, across contexts, across situations, right? And informed consent is important because at the end of the day what you're handling is user webcam data, which is actually highly sensitive data. So obviously they need to allow access and allow permission before the model starts taking the data from the webcam. Also, the data handling processes have to be disclosed along with the facts of, the model shouldn't be violating any fundamental rights, any privacy laws such as GDPR or CCPA. So yeah, you're also going to have to constantly monitor. I mean, basically, you're going to have to set up a continuous monitoring and alerting system that evaluates the prediction accuracy. So, what happens is if it notices that the confidence of the model is going low, so if some particular user, the model is not really able to gauge his expressions uh, or something, then what we need is either it needs to put a user in the loop. By the user I mean it need to put in a human agent in the loop. So for example, you have a chatbot which can automatically converse with people, okay, in video calls, and based on their expression, it can navigate, it can modulate its speech, its words, its intonations, so on and so forth. If this chatbot is actually noticing that okay, it is not that confident in this user, it seems to be getting angry but it's not sure, and it reaches the point where it's not really able to manage the user, it should be able to alert a human agent who can take over and then handle things from then on. And these alerts should be triggered automatically, right? So yeah, that must be done. It's also there's also something called data drift. Okay, what that means is if the data that your model, machine learning model, sees in production is very different from what it saw when it was being trained, then it results in data drift, right? uh, because suppose like you gave your model all well lit studio images when you were training it, and then when people actually start using your app or whatever, and the images from their webcam, the data is low light, or they're wearing glasses or masks which the model has never seen before, or from different angles which it does not work with, it will not perform well. And even though your training accuracy was high, your actual real world accuracy will drop, and that's data drift. Okay, so to make sure that there is no data drift, you need to constantly monitor. Okay, there is future scope. Okay, as I said, there are some more additional nuances and some more advancements which we are hoping to make. Nuanced emotions, for example, right? There are some complex emotions like disappointment, right? Like basically when someone is, so like it should be able to find nostalgia. How does nostalgia look? How does um, affectionate, sometimes people are affectionately being, basically should be able to understand bittersweet, expressions which are not one expression but are actually two or three expression, emotions colliding with each other. Like nostalgia is not just happy, it's happiness with a twinge of sadness, right? So on and so forth. Resentment, which is not only anger, it's anger and disappointment, right? uh, so on and so forth. So it should be able to actually understand. Sometimes you have frustrated admiration where you're frustrated because you're not doing well, but you're still admiring. Like an example, not exactly practical, but an example would be, when two sports players are playing against each other and one is just playing really well and the other is not able to, despite putting his all in, is actually not able to actually win any points. There you see frustrated admiration, right? So it should actually be able to identify that emotion for what it is, because you cannot just describe that expression as frustration or admiration. And that is where the model can actually not be sure that, what it is seeing. It cannot be so sure that is this frustration, is it admiration. So it should be able to figure out nuanced emotions. Enhanced accuracy, integrate, basically. The one of the most important points here is nuanced emotions and also temporal analysis, right? Sequential, that is why we are using ck plus, right? The model should understand how emotions evolve over time on the face of a human being. Some more points we have in future scope is per user calibration, which means every user, obviously every human being's expressions vary a bit. So having some idea of the user's face when it's neutral will actually really help the model understand, when I use, what are what. So basically it will help personalize its outputs for every user. Okay, this user does not display too many emotions, it's more wooden. Okay, so there it will pay more attention to some finer traits, and then some users are very expressive, right? So on and so forth. So it should actually be able to adjust itself based on the person it is dealing with. And for this you will have to have an onboarding, basically onboarding kind of ritual, where the first the user has to show his or her face through various angles at a neutral state. Multi-model integration, because what happens is you can't just observe the user's face. If they're typing, you need to also, like if they're talking with the chatbot, you need to also analyze their words. If they're speaking to the chatbot or they're speaking to whoever they're speaking to, you can also observe their voice gives you a good idea as to if someone's angry, worried, upset, happy. Voice also can play a big role in that. What words they're using, what is their expression. These three or four things combined together can give you a really accurate model which can be right more than 95% of the time, and can also detect nuanced emotions. Finally, you have continuous adaptation. There should be a continuous CI/CD pipeline which is continuously integrating, continuously improving, basically continuously taking feedback and input and adjusting itself and getting better over time. Right. So the more data you have, the better your model becomes, and that is our end goal here. There are some stress testing scenarios and tools that we have set up, or that we have ideas for, like real time inference. We should actually check if the we should our model deployment should at least be able to take 100 plus webcam streams simultaneously, where we are measuring the latency, right? If there is any delay, so on and so forth. Test our API resilience, so on and so forth, right? So these are some stress tests that we should be making sure that the model performs well on before we actually deploy it real world and say that okay, you can use this now. And that is almost all what I have. Apart from this is a basically an implementation, a very simple level implementation of how you can actually make something similar to this. Okay, not at this complicated level, because then this entire project is like a months long thing, but a very basic idea of, if you do want to create something like this, how would you start? Okay, and that I'll be showing now as well. So now for the practical implementation, which is basically what I'm going to cover here, is a simple implementation of a facial emotion recognition model. Okay, this one is basically created by Facebook. The Back in 2014, it's a CNN again, but it has 9 layers, so it's a 9 layer neural net created by Facebook AI Research, or FAIR. Okay, it was trained across 400,000 data points with taking using pictures of 4,000 to 40,000 people. And it actually achieved an accuracy of 96% back in the day on the LFW data, which is basically labeled faces in the wild. It's a benchmark test for emotion AI models. So there it achieved an accuracy of 96%, which is pretty high. It works with 3D modeling, which means it can actually work with 3D. So basically, since videos taken in real time have this 3D aspect to them, if you move your face and so on and so forth, it can actually work with that type of data, which back then was a pretty big deal. Let's just execute it. The implementation is much simpler nowadays. They have their own library from Deepface. You can just import Deepface, which is the name of the model, and then the rest is just normal CV2 dot video capture, basically just taking video from our webcam, right? Press Q to quit. This is just a debugging step to make sure that that the there is no issue in the webcam initialization, right? And we are basically retrieving the frames from what data is being read from the webcam. If not, then we break. Otherwise, we tell deepface to analyze the frame. Okay, what are we trying to analyze? The emotion. Okay, and then we get the dominant emotion, which is basically the emotion with the highest confidence score, right? So that is why we say zero, because the emotions are actually arranged in ascending descending order, and the one emotion which the model has the highest confidence that that emotion is being displayed in this frame by the user is kept at the top. So we are displaying that as the dominant emotion. We are then displaying that in text format using a bounding box on the frame, and then we're just displaying it. Okay. We also break the loop on q key. So if basically you press the key q, all the windows will close, including the webcam window. Okay, so let's try it now. Might take a second. Okay, and here it is. So as you can see, it's accurately detected that I'm neutral currently, but if I get sad or happy, it can usually detect, right? So as you can see, happy flickered there, but now since I'm talking once again, one of the issues with the model is it's not really good at working when someone's talking, right? But it's a basic model. It works to an extent. Whoa, that's miscalculated. So yeah, this is a basic implementation. Again, if you try to close the window, it won't. So you have to actually press Q. So yeah, that's all for today.